Welcome to the class. In this video, we'll use the concept of derivative to calculate the maximum or minimum value of various functions. We'll also find the turning points of the graph of a function and thus find the point at which the graph reaches highest or the lowest value. So let us get started. At first, we'll take this definition. It states, let f be a function defined on interval I, then f is said to have maximum value in I if there exists a point C in I such that fc is greater than fx for all x belonging to that interval. The number fc is called the maximum value of f in I, and the point C is called the point of maximum value of f in I. Let us see the example. These are our coordinate axes, x and y. Suppose this is a graph of a function. Let there be an interval from x equal to a to x equal to b. This is the function fx, and it is defined in the interval, close interval a comma b. This is the point C, and this is the value of fc, the height of this point from the x-axis. This point is c comma fc. Now if you observe the graph carefully, this is the highest point in this interval. This whole interval, this is the highest point. If you take any value of x, any value, this value or this value, or for that matter any value, for that particular value, the value of x will always be lesser than or lower than this value fc. So it means that this point is the maximum value of f. So the number fc is called the maximum value of f in E, and this point C, that is c comma fc, is called the point of maximum value of f in I. Similarly, B, f is said to have a minimum value in I if there exists a point C in I such that fc is less than fx for all x belonging to I. Now let us see this graph. Suppose this is x-axis and this is your y-axis. This is the graph of some function, and this function is defined, let us say, from x equal to a to say x is equal to b, and this is the graph of the function fx. Now here is a point x equal to c where the value of the function fc is lowest in its neighborhood or in its interval. All these heights are greater than this height. This is the smallest line segment amongst all these line segments. So the number fc in this case is called the minimum value of f in I, and the point C, that is c comma fc, is called the point of minimum value of f in I. Similarly, part C, f is said to have an extreme value in I if there exists a point C in I such that fc is either maximum or minimum value of I. Now let us solve some questions based on these definitions. Find the maximum and minimum values, if any, in the following function given by. First, fx is equal to 2x minus 1 whole square plus 3. Now, as we know that this is a perfect square, and the minimum value of this is 0. We know that 0 is the lowest positive number. All positive numbers are greater than 0. So the lowest value of this number is 0. So this function will have minimum value. This function will have minimum value when, what will be that minimum value? The minimum value will be 0 plus 3, it will be 3 when this term is 0, when 2x minus 1 is equal to 0, when x is equal to say 1 by 2. So at x is equal to 1 by 2, fx is minimum, and that minimum value is 3. Now as this is a perfect square, it will not have any maximum value because its value can go up to infinity. So this function will not have any defined maxima, but it will have a minima because the perfect square has minimum value 0. So the minimum value of this function will be 3, and at what point it will be 3? At x equal to 1 by 2, the function will have minimum value. Similarly, we can solve the second part. X square plus 12x plus 2, we can make it as perfect square. 3x whole square plus 2 into 3x into 2 plus 4 minus 2. This will become 3x plus 2 whole square minus 2. Now this function has become similar to the function given in part number 1. As in the first case, this is a perfect square, so it will not have any maximum value, but it will have a minima, and minimum value is 0. It will have a minimum value 0. The function will have minimum value of x will be 0 minus 2 is equal to minus 2. At what point it will have minimum? When this is 0, that is 3x plus 2 is equal to 0, x equal to minus 2 by 3. This we need not to find, we have to find just minimum value, and the minimum value is minus 2. Similarly, part 3, fx equal to minus x minus 1 whole square plus 1. Once again, this function, this part only without minus sign, this part x minus 1 whole square has a minimum value when x equal to 1 and its minimum value is 0. So rewriting this expression, we can write it as 10 minus x minus 1 whole square. The minimum value which we can subtract from 10 is 0. So the maximum value of fx will be 10 minus 0 is equal to 10. This function will have maximum value, it will not have a minimum value, because this number can be as big as we wish. The function will be maximum when we subtract the minimum from 10. Now the fourth part is gx equal to x cube plus 1. Now this number can take any value, howsoever big or howsoever small. For this function, maxima or minima does not exist. Graph will be like this. It will go up to infinity in this direction and up to infinity in this direction also. So this function will not have any finite maxima or minima. Now we'll see one theorem. Theorem 2. Let f be a function defined on an open interval I. Suppose C belongs to I. Be any point. If f has local maxima or local minima at x equal to C, then either f dash C is 0 or f is not differentiable at C. Let us see what it means. See this graph. Suppose this is a function like this. So these points will be called local maxima. This is the highest point in its neighborhood. This is the highest point in its neighborhood. And here also, this is the highest points in its neighborhood. So these are the local maximas, max 1, 2, 3. This point and this point are the local minima. If you draw the tangent at these extreme points, that is local maxima or local minima, the tangent will be parallel to the x-axis. So at these these extreme point, the first derivative will vanish. This will be equal to 0. Or when the function is, or when the curve is taking sharp turn like this at this point, or at this point, these points will also be maxima or minima. This point is maxima, this point is minima. At these point, we know that the function is taking sharp turn, so derivative is not defined. The first derivative here and here not defined. In previous chapter, I have told you that at cusp point means where the curve taking a sharp turn is called cusp point. At these point, the first derivative is not defined, but these may be local maxima or local minima. This is the point local maxima and this is the point local minima, but the derivative is not defined here. So this is minima and this is maxima, but we cannot find or we cannot define the derivative at this point. This is what the theorem says, but its converse is not true. There may be some point where the first derivative vanishes, but that point may not be local maxima or local minima. See the graph of fx is equal to x. See, this is the graph of fx equal to x cubed. At this point, tangent will be like this. Tangent will be parallel to x-axis, that is first derivative will be 0, and this is the graph of fx is equal to x cubed. But this point is not local minima or local maxima. What is happening is the graph in this region graph is increasing. This region graph is also increasing, but in this region graph stops increasing, but it is not decreasing. It remains constant for some moment and then again start to increase. Such points are called points of inflection. If you observe carefully, you see the graph is changing its concavity. When the graph is below x-axis, it is concave downwards like this. And when graph is above x-axis, it is concave upwards. So it is changing its concavity, but this point is neither maxima nor minima. So such points are called points of inflections. Theorem number 3. See the graph of this function. This point is the local maxima because this is the highest point in its neighborhood. Suppose we draw the tangent at the maximum point. This tangent will be parallel to x-axis, that is dy over dx will be 0, or the first derivative of the function will vanish at this point. Now, if you draw the tangent just before this point, here it will go like this. Now, if you extend this tangent here, you will see that this angle is an acute angle. And if you draw a tangent just after the maxima point, tangent will go like this. This angle will be obtuse angle. Now we know that the slope of the tangent m is equal to dy over dx. So at this point, dy over dx will be positive because tan theta will be positive. Why it will be positive? Because acute angle lies in the first quadrant. All trigonometric ratios are positive in the first quadrant. But at this point, dy over dx will be less than 0. Why? Because all obtuse angle will lie in the second quadrant. And in second quadrant, tan theta will be negative. So maxima point, the value of the first derivative, first it is positive, then it becomes 0, and then it becomes negative. First, the first derivative is positive, then becomes 0, then becomes negative. It means that at maxima point, first derivative decreases. dy over dx decreases at local maxima. dy over dx decreases at local maxima. Similarly, see the graph of this function. Now, if you draw tangent at the local minima point, obviously this will be 0 first derivative because the tangent is parallel to the x-axis. Now the graph just before this point is say x equal to c. Just before x equal to c, if you draw the tangent, it will go like this. It is making obtuse angle with the positive x-axis, and at a point just after c, just greater than c, or we can say at c plus h, at this point x equal to c plus h, if you draw a tangent at this point on this graph, it will go like this. This angle is acute angle. We know that m equal to tan theta, or dy by dx is equal to tan theta. So just before the minimum point, dy over dx is less than 0 because this angle is obtuse, and just after the minimum point, dy by dx is greater than 0. And obviously at minimum point, first it is negative, then it becomes 0, then it becomes positive. Means it is moving from this point to this point. It means at minimum point, dy by dx increases. Let's revise it. At minima point, the first derivative becomes negative to positive through 0, and at local maxima point, the first derivative becomes positive to negative through 0. But this is not the case at the point of inflection. At point of inflection, the first derivative does not change its sign. See the graph. The blue graph which we are seeing, that it is the graph of f equal to x cube, and the red graph is its first derivative, that is 2x square. See, 2x square, that is the red graph, does not change its sign because it remains totally above the x-axis, and we know that above x-axis the y value or the value of the function is always positive. So at point of inflection, the first derivative does not change its sign. It becomes 0 for some time, but its sign does not changes at the point of inflection. Whereas at maxima point or minima point, the sign of the first derivative changes. At maxima, the sign of the first derivative changes from positive to negative through 0, and at the local minima point, the sign of the first derivative changes from negative to positive through 0. But at the point of inflection, the sign of the first derivative does not change, as in this case. Let us see once again. See the function y is equal to x cube. Find its first derivative, dy over dx is equal to 3x square. Now dy over dx vanishes at x equal to 0. Let us take a value which is slightly less than 0. Say dy over dx, let us find it, x is equal to 0.01 minus negative. X equal to negative 0.01. The value will be 3 into minus 0.01 whole square. It will be 3 into 0.0001. This value will be 0.0003. It is positive. Now let us find dy over dx When x is equal to say 0.01 positive value, just right of 0, this value is just left of 0, and this value is just right of 0, greater than 0, it will be 3. 0 0.01 whole square, 3 into 0.010001, it will be 0.0003. It is still positive. So at x equal to 0, dy over dx is 0. Before this, dy over dx is positive, greater than 0, and after this, on the right hand side of 0, it is still positive. So the sign of the first derivative does not change at the points of inflection, but at the minima point it becomes negative to positive. At maxima point it becomes positive to negative, but at point of inflection the sign of the first derivative does not change. Now let us see the second derivative test. Let f be a function defined on an interval I and c belong to interval I. Let f be twice differentiable at c. Then first, x equal to c is a point of local maxima if f dash c equal to 0 and f double dash c is less than 0. The value of fc is local maximum value of f. Let us see how it works. At local maxima, the first derivative becomes 0 at the point of maximum value. At this point, the first derivative becomes 0. Before this, the first derivative is positive. Dy over dx is positive. At this point, it is 0. And after this, the first derivative is negative, as we have seen in the previous video. So the first derivative becomes negative from positive. It means that the value of the first derivative is decreasing. Previously it was positive, then it becomes 0, then becomes negative. Previously it was positive, then it becomes 0, then it becomes negative. It means that the value of the first derivative is decreasing at the point of maxima. At maxima point, the value of the first derivative is decreasing. That is why the second derivative is negative at the maxima point. So if the first derivative vanishes and at that point the value of second derivative is negative, it means that the point is local maxima. Similarly, see the local minima point. At the local minima point, the first derivative vanishes, that is dy over dx is equal to 0 at this point. Before this point, the first derivative is negative. After this point, the first derivative is positive. It means that the first derivatives, previously it was negative, here it is negative, then at this point it is 0, then it becomes positive, means it is becoming positive from negative through 0. It means that the value of the first derivative is increasing. If the value of first derivative is increasing, it means that its second derivative should be positive. So at local minima point, first derivative will be 0 and second derivative will be positive. Why positive? Because at this point, at local minimum point, first derivative is increasing from negative to positive. And the second derivative test fails when first derivative is 0 and second derivative is also 0. We'll make use, at this point, we'll make use of first derivative test. We'll see at this point, first derivative is 0, we know that, and second derivative is also 0. We cannot make conclusion using the second derivative test, so we'll rely on the first derivative test. We'll see if the first derivative is positive before this point and negative after this point. If this is the case, it means that it is local maxima. If the first derivative is negative before this point and positive after that point, it means that it is a local minima. If the first derivative does not change its sign, it means that this point is point of inflection. Now we'll see working rule of finding maxima and minima of a function. Step number 1. First find the all critical points of the interval, that is, we'll equate first derivative to 0 and then we'll find the corresponding value where the first derivative vanishes. Step number 2. If the function is defined in the closed interval, say AB, we'll find the value of the function at these endpoints, that is fa and fb. If it is open interval a comma b, we need not to find the value of fa and fb. Step number 3. Find the value of the function fx at all critical points and endpoints if the function is defined in the closed interval. Step number 4. Out of the above values of fx, identify the maximum or the minimum values. The highest of the values of fx will be called absolute maximum and the lowest will be called the absolute minimum value of f.